I know that. Let's say sometimes you may need it. So just in case. Okay. So let's say the projection matrix, for example, we have, so what do we mean by projection matrix? I know that you all remember, but just put it down here. So you have the OS beta hat is equal to X transpose X to the minus one X transpose Y, right? And you want to have Y hat equal to X beta hat, is that right? It is equal to X transpose X transpose Y. The matrix here is known as the projection matrix, right? Now, and then I minus Px is equal to Mx. Mx is also a projection matrix. So when you have Px, it is a vector. Let's say if you have a vector y, that is, this is the table is the space of the explanatory variable. If you have the dependent variable in the on the surface of the table, what happens? That's it. If you project something into the space of itself, you predict perfectly, no residual, right? So if you regress a column, you have a vector X, a matrix X of many columns, you regress one column of that onto the whole matrix X, you would predict perfectly because the coefficients of the X within the matrix will be equal to 1. The coefficients of all the others will be 0. So if you use X to predict itself, it will be itself. Never a mistake at all. But if the dependent variable is out of the space, you have to project it to the X matrix space, right? So everything you can predict is this part, but not the part from here to here. The part from here to here is orthogonal to the table surface, and the space that is orthogonal to the X space, X matrix space is known as the MX. Right? So it projects orthogonally. This one projects Y orthogonally to the space of the expanded by the X matrix. That's the idea, right? So this MX is also a projection matrix. So the second result is that if you have a matrix Z that is standard normally distributed but independent of each other, and you have a projection matrix, then Z transpose BZ is distributed at chi-square with R degree of freedom. So these are the two results that normally plays a very important role in many of the econometric results, right? So let's stop at that and move on with our ongoing discussion. So what I'm saying here is, I have a vector M. This vector M has a mean of 0. M is a function of beta hat. Is that right? Beta hat is normally distributed, so M is also normally distributed. The variance is this one. So I just apply the first theorem of the chi-square. So X transpose X transpose omega to the minus 1 X omega square with M degree of freedom. Remember that theorem number 1. So this is my M now is my X. Right? M now is my X. So M transpose the variance of M given X to the minus 1. This is omega. M will be a chi-square distribution, and its expression is here. Right? We need to remember. So, okay. Ladies and gentlemen, so if the null is correct, W will be a chi-square distribution. Is that right? With J degree of freedom. The problem is that we can never compute this ugly one, right? So we have to replace it with something else, right? If we replace it with the sigma hat square, then we will turn it, and there will be no time to go deep into that. But we replace it. So let's say we will follow the step to replace it with the sigma hat. Then actually we are dividing so we will end up having a formula that f is equal to let's say w over j, sorry, divided by a chi-square with n minus k degree of freedom divided by n minus k here. So you have the ratio of two chi-square rescaled by their number of degrees of freedom. You end up having the F distribution, right? So by definition, what is a T distribution? A T distribution is the ratio of a standard normal divided by the square root of a chi-square rescaled by its degrees of freedom. A F distribution is the ratio of one chi-square divided by its degree of freedom over another chi-square divided by its degree of freedom. So we have the chi-square. It follow a chi-square, right? Good. So if the null is correct, you compute the f, and you will end up having it to be to follow an f distribution. Now, so that's this. I will go quickly. This is where we need to use in order to compute something in our regression. So the test before was for general purpose. Right, this one is for the general purpose. That is to say, we want to test R times beta is equal to Q. But now we want to test a very specific case. That is when we want to test that parts of the beta hat are not zero, are zero, right? Part of the coefficient here are zero. So let's say in our regression table, we want to test, except for the constant term, all other beta 2 are zero. But in other contexts, we may test part of that. So in our regression table, the x1 here includes only one thing, that is the constant, right? Other variables are put here. Okay. So how can we test that? So let's say we can go with, again, we suppose that the beta 2 is correct. So we compute the error sum of square, which is equal to this one. And it could be written as equal to y transpose mxy. Now we consider the full model with epsilon as the error term. And we apply the Fitzgerald-Lobel theorem, right? So something that we already discussed a lot. And we can compute beta hat 2 equal to this one. And we substitute it back. So ms1 times mx1, y is equal to this quantity. And after some manipulation, you will see that the epsilon hat transpose epsilon hat is equal to expression. So the residual sum of the restricted model will be equal to this component plus the residual sum square of the unrestricted model. So this one is E1 transpose epsilon hat 1 transpose epsilon hat 1. Here is epsilon hat transpose epsilon hat. So if we have this result, we consider this term. Yeah, you take the difference between the total sum of square of the restricted model minus the total sum of square of the unrestricted model. You have this one. And after some manipulation, you will see that again we will have x2 transpose mx1 times epsilon is equal to let's say the difference between the two error terms will be equal to this one. So right, so this is the part, and you notice here that there is a term that is x2 transpose mx1 epsilon. We consider this component here. So it is normally distributed because epsilon is assumed to be normally distributed. Its variant covariance matrix is this one. So this one, if we apply the theorem on the chi-square, it will follow a chi-square with n minus k degree of freedom, right? So the f in this case could be written in this one, and after some manipulation, it will be written in this one. Okay. So if you know the punchline, if you want to compute the hypothesis test that part of the coefficients are zero, first you run the restricted model, remove the variables that you suspect their coefficients are not relevant or they are zero. You run the model, you get the total sum of square. You run the full model, you get the total sum of square divided by r, and down here you take the sigma hat square. This one, following our proof, follow an F distribution with r and minus k degree of freedom. So now a special case. If you consider this one, if you consider this one to be epsilon hat 1 here, is the error term when you have only a constant, right? So epsilon hat 1 is equal to m1 y. Is that correct? Because you only regress it on the constant. Okay. So let's say epsilon hat transpose epsilon hat 1 is nothing more than y transpose m1y. Is that correct? Agree with me? Now, because this one you only have the constant. So this is a total variation in y, right? This is the error term in the full regression model. This is the total variation at the error term in the full regression model. So now I divide both the denominator and the numerator by this quantity, right? So I will get this is equal to 1. Is that right? Okay, so let's say I would take now. So epsilon 1 hat transpose epsilon 1 hat divided by epsilon minus epsilon 1 hat transpose epsilon 1 hat minus epsilon hat transpose epsilon hat over epsilon 1 transpose epsilon 1. This one is nothing more than y transpose m1y. Is that right? So you have nothing more than here. It is 1 minus epsilon hat transpose over epsilon hat over y transpose m1y. And this one is nothing more than the r square. R square. Is that correct? Yeah, square. Okay. So this one, if I divided both the denominator and denominator by this quantity, then I would have here, I would have the r square over r. Is that right? And down here, I would have epsilon transpose epsilon, epsilon hat transpose epsilon hat divided by this one. So it is nothing more than 1 minus r square. Okay, so this one will be equal, f will be equal to let's say r square over r divided by, over here you would have 1 minus the r square divided by n minus k. Good. So r here now. If we are talking about the special case, when we test for the hypothesis. Now let's say we test for the hypothesis that say I need to take the pen, right? Where is it? The pen. Oh, here. The pen is here. Draw, and I take a different color. Right? Let's say now. So let's say for the special case here, we have r square over n minus over k minus 1. Is that correct? K minus 1, because this is the number of explanatory variable except the constant term. Over here, you would have 1 minus r square over n minus k. This is k minus 1. K minus 1. So in order to compute that F statistic in the regression table, you would take r square over k minus 1 divided by 1 minus r square over n minus k, and this one will follow a chi-square, an F distribution with Rn, with k minus 1 and n minus k degrees of freedom, right? So this is a long discussion, but just to compute something that is quite quite simple here, right? So this is how we can compute the F. So the F stat is equal to R squared divided by the numerator degrees of freedom, okay, divided by 1 minus R squared over the denominator degree of freedom. The denominator is n minus k. This is k minus 1. So by teaching you Python programming, you just do this computation. But if we do not derive it, I don't know how to do it. So basically, whatever you want to compute, you must know how to compute it, why you compute it, and how to compute it, right? And if once we know how to compute it, why to compute it, we can always do it. So again, here we are. Oh, I'm sorry. If I do this, the link will not be able to hear it. So the purpose here is that we learn Python, but it must be based on something. And in our case, we base it on economics. Now, so in that case, I am actually kind of reviewing some simple econometrics knowledge. And I encourage you guys to go through the slides because it's not an insult to your intelligence. But if you happen to be a PhD student, somehow, some way, the first thing you have to teach is this one, right? Because you have to teach basic econometrics, and they are here, right? The idea that you should remember. The p-value, okay, again, right? The p-value, again, this one is an example. This one is an example of a one-sided test. Because the F is equal to the 2 chi-square divided by each other. It can never be negative, right? So it can only be positive. So if you compute something, you only focus on 1 minus the CDF. Get it? So, you type this one, or you don't type it, I don't know. But this is how we use Python to program the F statistics, right? So there are two ways of teaching it. One is go with the math and then show you how it can be done this way. The other is write it down this way and you ask why and start with the math. But that's right. There's no way that we can escape the math. Right. Good. So right, that's for your attention on that. Now the other stored values are here, right? So let's say now we do not care that much about the component here. So let's say this part we don't care, right? Now we need to talk about this one. Now the probability here we already did it, right? Now this one is the log likelihood, the AIC and the VIC for me. We have to do this. right? So let's say how to compute the AIC. If I don't talk about maximum likelihood, I can give you the formula, and it you just say be frowning and say what's that? Okay, so we need to do something. We need to do something. But before we do something like that, can we give some kind of confidence boosting by showing that okay, this one by computing it, we would get the same results. Oh, not yet. Now I want to show you what I want to show you. I want to show you that our estimates are very much similar to the one in the table. Yeah. Oh no. Now I do print model dot results summary. Okay. Oh. A summary, is that correct? So what I'm trying to tell you is, it took a lot of efforts to show the math, and then we put the computation into Python. We get the F statistic here, right? The F statistic is defined as equal to this one, right? The F statistic here. We get the result, and it is exactly the result here. The p-value here, it is that. Okay, fair enough. So then let's say, if you want to program, you must know what to program. And in order to know what to program, the only way is to study and get the knowledge. No? Okay. Good. So I am almost done with the first set of slides, right? So let's say all of the steps, one way or the other. So sometimes I include the kind of proving here, right? But I don't mention it because I would assume it to be too simple. Right? But let's say this morning we did this, right? This morning we did this. But let's say this is a simple showing why we have that the estimation of sigma hat square is equal to this. Get it? This is the idea that we had in the morning. We already did it. Inference, the estimate, and the like. So you have to go through it and to remember those. Yeah. So this part. Out of so I just include for your information, right? But you have to remember a t. What is the definition of a t? Right? What is the definition of a t random number? The t random number. It is the ratio of the t distribution, not the chi-square, right? The t is a ratio of a standard normal divided by the square root of the chi-square rescaled by its degree of freedom. One condition is there. The z and the chi must be independent in order for it to be a t distribution. And here is the proof that they are independent, right? So please have a look at it. So I am going from one side of econometrics to the other side of statistics. So it will be a lot of knowledge here. But sometimes I think it's important to include it. I already included, right? So these are all we already discussed. One thing that we have not done, but it will be your job, is to compute the confidence interval. So let's say, please do the computation, because that would be part of the regression table. Our goal is that we will compute everything, right? So this is the lower and the confidence at the upper level and the lower level. We need to compute it, and the formula is here, right? So the formula is very simple. You take beta hat k minus the critical value c times the standard error. So in order to do that, now I look at your eyes and I don't think that you are very prepared to do that. You program that. Okay. You program the upper and the lower confidence interval. Okay, good. Please do it. I think if you do it quickly, it's in 1 minute. You already have the T, right? You remember that? You have the T. Can you all program it? So remember that we have the T somewhere here. Where is it? R square. Oh. I think we have the standard error here, right? How can we compute the T? We have the standard error here. The T statistic is here, right? Is that right? So now we need to compute what? We need to compute the confidence interval. Right? So let's say how to the p-value. We already talked about that. Let's say we have the t-stats already. The r square we already did it. The f test. Now we need the okay. Now I put one more term here. That is to say, let's imitate the whole practice, right? So let's say here the confidence interval. Now, how to compute the confidence interval? So we would have lower. Is that correct? Let's follow the common sense, right? The lower will be equal to what is it? Beta hat. Is that right? Oh, sorry. Beta hat. Thank you. Minus what is it? T stats, right? Times. Mm-hmm. No. Okay. Let's check. Okay, that's the right one. Times what? You know the standard error we have? Which one? Did we denote it? No, we did it somewhere. Now you have to read. You have to call exactly what you have named, right? It is standard errors. Is that correct? Mm-hmm. So we have all the ingredients that we need. All ingredients that we need. So it will be this one. Is that right? Okay. And the upper would be it. Would it work? Now, in order to make sure that to check if it works or not, you have to check if for the t-stat it is an array, right? Yes, that's good. That's okay. For the beta hat, it is an array. I remember, so it cannot be wrong. Okay. And then for the standard errors, it is an array. Is that correct? So if you run this one, you think that it would work? What do you get? You get no complaint, right? That's lucky. Now, whether you get the right, whether you get what you intended to get is a different question. Now, so let's program again the upper. Right? Let's say the upper is too easy, right? Upper. Right? Oh, I'm sorry. This is upper. Right? Okay. So now you want to print it, is that right? Or do you need to turn it into a data frame? Okay. It's fine? Print it. Now let's say lower and then upper. So let's say if they will give you the right answer. See, it's not working. So you need to, if you want 2 rows, you have to turn it into a data frame. Okay. So let's say now, if we are, so let's say if we are lazy, then we just go to ChatGPT, say, put them into a data frame. So I can print them as columns, right? Okay. So now it's I did this and I repeat what I have been saying so far. Now we need to do the so-called eyeballing methodology. Look at it and see, in order to create it, right? So we have to create a new data frame, right? With an open parenthesis and a closed parenthesis. Within it, we will have a what's this? The curved bracket, and we have the estimate, beta hat. We have the lower bound. So these text will be printed and upper bound. So let's say in this way, in the data set, this one will be the head, this one will be the head, and this one will be the head. If we run that one, we will have a new data frame, right? So let's say CIDF. Where is it? It's something that is okay. So what do we get here? Per column arrays must each one dimension. I see. There is a problem. One dimension. So we have to flatten it first, right? So let's say if we face this problem, normally I would continue to copy it and put it here. It won't be fixed, right? We have to flatten it. So this is what will be done, right? So here it means that we need to provide, we have to change them into the object that has dimension, so that it could be printed. So let's say paste. So make sure inputs are in one dimension array, right? So let's say we convert them all. And hopefully that we get it right now. Yes. So this is what we would have, right? So we'd have estimate the lower bound and the upper bound. And I'm pretty sure that they are. Let's just see the one before. Now, so what is the say the original variable, right? Let's say I need this one. No. Yeah. Ha ha ha. The confidence interval that we have computed is not correct. the lower bound and the upper bound. It is not correct. Something is wrong here, right? So let's say, and that's why I said at the beginning, be careful. Maybe you will not get what you intended to get. Sometimes we are lucky that the software says, no, I can do that. There is a mistake. Sometimes it quietly does what you want and give you a wrong answer. Right, so what is wrong here? So the way we have computed the confidence interval is somewhat not correct. So when we input it in this way, something has. So let's say with this way of computing, it should be 5%. That's correct. That's correct, right? So we need to have the value of the critical value, right? Okay. So what is our degrees of freedom here? What is our degree of freedom here? It is, right? So it is 8,980 degrees of freedom, right? So we would need to compute the critical value of a t distribution with 8,980 observation. So let's say we will compute the critical value of that, right? So let's say if I say, give me Python code to standard normal. Fine. But let's move it this way, right? So let's say after 1,000 or so, we don't care that much. Yeah. So give me the Python code to compute the critical value of a t. Now let's say when we say critical value here, we have to say 95%, right? 95% critical value of a t 8,980, right? Okay. I already turn off the sound. Can it be from Khánh Linh side? Okay. Let's say the first thing we need to do is to compute the critical value, right? So good. And then now we will need to take the critical value. Is that correct? Minus this one and minus this one. Okay. Good. So let's do it again and see if we come up with the same answer. I have. Oh, no, I have not. Sorry. No, I think, yeah, so let's say, I think, no, this is, yeah, so let's say we have this one, it should be critical value. Critical value. And let's say no more mistakes, right? Good. So let's say now we want to compare with what we have, right? Good. So ladies and gentlemen, do you think that we have the same? Good. Okay. So this is just an example of what we think that we are doing. there is a danger. I mean, if we have a mistake and it's red, we know how to fix it. But if we do not even know that we are making a mistake and the software just gives us the number, that is more dangerous, right? But basically that is Python programming. So let's say there is no guarantee that I don't ask you manually compute the confidence intervals of the estimated coefficient, or sometimes I would say of the 99% confidence interval. What's that? So let's say I don't ask you let's say, to be honest, to learn by heart everything, but at least you must know the steps like this one in your examination, basically. Yeah. So that's what to expect. That's what to expect. So it could be very much stuck. So what I do, I give you the same data set. There could be some estimations, and then you will be computing some statistics, and you need to do that without the internet, right? Without the internet, and I don't prevent you from using your own stored file. Okay, let's say I even think of giving you the opportunity to bring in 2 A4 sheets of paper. You write whatever you want of all the commands. Now, because when I allow that, I would include so many questions that that will not be the case that all of you can do by reviewing your A4, right? But you must have some, I mean, the message here is you must have some understanding of the syntax. You must remember at least systematically how the steps are done. You may not be able to type things in an exact way, right? But let's say, and then you have to refer back to the A4 to see, oh, this is the CDF of the F distribution, how it is written, right? Or this is how to draw a chi-square distribution. But if you do not remember the steps, you will not be able to finish the exam within 60 minutes. Good. Sounds fair. Happy. Done too. Yes. Right. See. So let's say you have to do eyeballing quite a lot just to remember, right? Just to remember the steps, right? So let's say something that I thought was easy, then it also took some time to get it done. But basically, this is what we mean by programming, right? In order to program, we must know what is there. And if we know it's wrongly, we compute something that is wrong, right? So we and I try to compute something that was wrong. And then we turn back to see, this is wrong. But that's how things work, right? Okay. Okay, so now, because of my promise that we would compute, I mean, in the end, we will not be compute everything, but let's say now we have the AIC and the BIC, right? AIC and the BIC. So this is just a piece of cake with you guys because you already did much more comprehensive things. But let's say the Gauss-Markov theorem, let's say something that I have already included here for your information, even though you did the pre-master course. But let's say what I want to emphasize here is something I said in the morning. So something that is important, I touched one time and I will repeat another. So now it's the repetition. So if you are in the Khánh Linh in the morning, this is what I talked about. So if you missed it, now I'm talking on the screen. Yeah.
The morning.
Yeah, when I was talking
the Friday.
about last number. The last number
yeah.
I draw on the board. Yeah, I draw on the board. This is what I mean by probability limit, right? So in the morning I try to use the body language, even though I don't have that beautiful body. But the idea is the body language to give you an intuition about what I mean by the probability limit. And now it is formally defined this way. a statistics that is the probability limits here means that when it has we have a series of data, if the number of observations increases to infinity, what do we get, right? So let's say if x is a series and xn and yn are two series, then the probability limit of a sum is the sum of the probability limit. This is similar to the limit. The limit of a sum is sum of the limit. Fine. Different. Nothing to complain. This is a nice thing, right? So probability limit of a product is the product of the probability limits of a ratio is a ratio. The limit, of course, when it is not zero. So the nice thing is, let's say if the probability limit of x times y will be equal to this one, right? So the probability limit of the inverse is equal to the inverse of the probability limit, right? So this is very important. Probability limit of the inverse is equal to the inverse of the probability limit. So these are the results we said in the morning. For example, if we think of the matrix X transpose X, right? X transpose X, and if we multiply them, and you will see that each of them here is a summation of entries, right? So if they are IIG, meaning that they are not too dependent, and they don't have a variance that is go to infinity. If you have a series whose variance go to infinity, the problem is when you draw one, it could be small, the other could be infinity. So you would never have a conversion. You get it? So we need it to be identical, meaning that the variance doesn't change. Get it? Dependence, I said in the morning here, let's say if you have identical, meaning that you have the same variance. When we talk about independent, if something that is dependent, if it happens, if the other term happen to be positive ones, because it is dependence, it will be positive all the time because they are dependent, right? So sometimes another shock down here, it will be negative all the time. So there is no guarantee that they will cancel out each other. But if they are independent, if someone is here, one observation is here, the other likely to be here. Or maybe here, but then it is random. So the randomness will cancel out each other when the sample is large. So independence is required for the large number, right? So the randomness will cancel out when they are independent. Because when they are independent, you do not know the sign of the randomness part. Okay? If they are dependent, if you know one is negative, you know the other will be negative. Or if they are negatively dependent, if you know one is positive, you know the other is negative. And when that is the case, the randomness will not cancel out. Right? In a small sample, maybe the randomness are still there because there is not enough observations to cancel out all of that. But if the sample goes to infinity, all of the randomness will be cancelled. Yes. Right? Okay. So that is the case, right? So now I come to a very challenging problem, right? You spend 15 seconds on preparation of something that is that need a lot of reasoning. Let imagine now that I split my explanatory variable matrix into two parts. The first part includes only the constant term. Okay. The second part includes all other explanatory variables, and I will use the Fitzgerald value. So the first, that means I will delimit them all, right? And my matrix X now it no longer contain the constant, but it's just only the axis. That's the variation, right? So you will see that in that case, if I delimit them already, then this one will be the variance. This one will be the covariance. Is that right? So if the sample goes to infinity, this matrix is nothing more than a variance covariance matrix of the explanatory variance. Okay, I hope that you, if not, I presented clearly in the text. Read it. But the idea is that if you have a constant term, okay, then the X transpose X here is nothing more than a variance covariance matrix of the explanatory variable. So if you have a very large sample, you will have their variance covariance, right? That's the idea. So it will converge to their variance covariance if the sample is large. And their variance covariance are assumed to be constant. So when the sample is large, this one is like okay. That is 100% correct, but not necessary. What is what is the value of infinity minus 1? So what you are saying is 100% correct, but it is vital in the small sample. Yeah. No, when it comes to large sample, even for when we do, let's say when we do the maximum likelihood, we don't subject either. It's so let's say when the sample is very large, we ignore that. But we have the point, right? So let's say you have to correct for the fact that you have estimated one parameter here, that is the mean of x2. So the number of degrees of freedom now is not n but n minus 1. So it should be n minus 1 here. But that would create a lot of problem later. If I want to put the others, it will mean it makes things longer. So I do this one. Yeah. Okay. You get what we asked for, right? Okay. So basically, what I want is this in the morning, right? So if I have this one, again, I am using the result. The probability limit of the inverse is the inverse of the probability limit. So I have this one. Okay. It is a constant matrix. I have this one approaches 0. So the result of beta hat I said in the morning will be equal to this one. And if the sample goes to infinity, this one is a constant matrix. This one is 0. So it will be equal to beta. Now the danger here is if the sample is not large enough, this one, there is no guarantee that this one will be 0. And if there is no guarantee that this one will be 0, there is no guarantee that you have the beta. Get it? Clear? Now your job is to demonstrate that. I want you to be able to do this. Now this is the task. Now, so let's say I just simply repeat what I said in the morning. But let's say now you need to implement this idea into Python. And I want you to show, this is the problem, right? So let's say, suppose there exists a variable yt, okay, which is dependent on xt by the following data generating process. Okay, and you take beta 1 is equal to 4, beta 3 is equal to 3. Simulation exercise can be done in the following steps. 1, a simulated population of 20 billion observations is generated. Okay. 2, the first samples of sign n is drawn from the simulated population, and beta n1 is estimated and saved. The second sample of psi n is drawn, and beta n2 is estimated and saved. The process keeps going until the 5,000 sample is drawn and 5,000 betas are estimated. Estimate the plot and plot the empirical probability density functions of beta hat n. Repeat the process for different sample size n. In our case, the sample size are 100, 200, and until a million. Plot the result PTFs in a single graph to visualize the probability limit of beta at n. This is a problem, right? And your job is to do something until you get this one. Yeah, until you get this one. Okay. So when you look at this one, you see, this is the example of the law of large, the application of the law of large number in the context of linear regression. Is that right? Yes. Can you do that? There is a theoretical derivation in our problem. You need to implement in Python. Anh Linh, you are with us?
Yes, yes.
Okay, please, you see the problem, right? You see the question, right?
Yes, yes, yes. I capture it.
Okay. This could be an examination, an example in an examination. Demonstrate the law of large number, the consistency, and this is known as the consistency of the OLS. Làm lại con kia đây. Chưa hả? Copy chứ cái đó vứt vào chat GPT, bọn mày làm cái này không thể đâu nào. Nó làm cực nhanh nào, có vấn đề gì đâu nào. Xong thầy muốn nói là ngày xưa ta đi cần so cái manual, còn bây giờ ta cần so cái gì? Rồi, thầy chỉ sửa một xíu thôi này. Chỗ này mà các bạn làm 20 million và các bạn simulate này nó sẽ mất 2.000. Bởi vì thầy yêu cầu là ước lượng 5.000 lần đúng không? Mỗi một lần draw 1 triệu observation rồi làm 5.000 lần là nó. Thầy khi mà thầy làm cái graph này là thầy phải để nó chạy rồi thầy để máy chạy rồi thầy về nhà hôm sau thầy lên thì mới lấy được kết quả, đúng không? Đó. Cho nên là thôi các bạn sẽ giảm nó xuống là các bạn tạo 200.000 observation ở đây thôi và làm cho đến 1.000 thôi. Đấy, nhỏ thôi. Đó. Lên làm đến 10.000 đi nhá. Đến 10.000 thôi. Được không? Hiểu thầy nói không? Tức là chỉ cần tạo lại cái này cho thầy là ok rồi. Lại cái này thầy là ok rồi. Đây, khi mà thầy graph cái này thầy nói lại lần này, khi thầy graph cái này là thầy buộc cái đoạn này đến đây này là nó phải bằng từ đây đến đây này, để thầy nói với các em là khi mà sample nó lớn là cái variance của nó làm sao, nó nhỏ lại, nên gọi là converge in probability. Lại bị trẻ. Đấy, thầy chạy sang thầy để đó thì mình nhà cho mình. Nhưng mà các em hiểu ý tưởng không nhỉ? Đấy, cái problem là cái problem nào các em phải solve là như thế nào? Sao rồi? Thế nào rồi? Nhớ là ở nhà là phải eyeballing nó để xem từng cái bước nó nha, chứ không có lên lớp thi là không thi được. 2 trang A4. Ok. Không áp lực làm sao được, đi học phải áp lực. Nhớ không, lúc nãy có bạn nào không trong lớp không nghe về 2 4 6 8 9? Linh nghe chưa Linh? Mình các bạn sẽ được cầm 2 tờ A4 các loại function của Python mang vào lớp thi. 2 tờ, tha hồ mà ghi. 4 mặt anh ghi thoải mái. Khi mà thầy mà đã cho ghi thì thầy không bao giờ, thầy sẽ không bao giờ hỏi cái mà các em đã ghi.
Ủa, thầy là mình thi giấy hả thầy? Em tưởng mình thi trên máy chứ.
Thi trên máy em đúng rồi, nhưng mà thầy không cho dùng internet em.
Nhưng mà mình cũng lưu được mấy cái công thức.
Các em có thể làm mấy công thức đó em có thể để ở đâu cũng được, nhưng mà thầy nghĩ là cái việc ghi ra thì nó sẽ nhớ là một, đúng không nhỉ? Thứ hai là không biết học lại mấy trước nó cho thi thế nào mà thi máy vẫn cho mang ấy vào nhỉ? Thì bên chắc là bữa nay thầy không cho mở ra. Ý của Khánh Linh ở đây là em muốn ghi 40 trang em giấu ở trong máy của em chứ làm gì em, đúng không?
Dạ không, ý là do cái hồi thi Stata của thầy Binder là không có kết nối internet đó thầy.
Ok, còn lại là muốn dùng
Dạ
cái đó
nhưng
thì dùng, đúng không?
dạ nhưng mà tụi em có lưu sẵn mấy cái code ở trong mấy cái file data á thầy.
Ok, thầy hiểu rồi. Thầy hiểu, cảm ơn câu hỏi của
Dạ.
em. Vậy thì thầy về đấy là cái việc test. Không không, bây giờ thầy mà test những cái thứ mà đã viết đây thì nó sẽ không hợp lý, là không thể test ứng dụng thôi à. Tức là thầy ứng dụng ở bối cảnh hoàn toàn khác. Và nếu mà không nhớ những cái này thì không làm được cái đó, đơn giản. Tức là ý thầy ở đây là thầy không không bao giờ ra đề để các em copy lại đúng cái thầy làm trên lớp xong bỏ vào đấy xong thì nó vô nghĩa lắm, đúng không? Cho nên là trường hợp này với lại thứ hai là khi mà đã cho mang máy như vậy thì cái số lượng câu hỏi nó sẽ đủ để các em ở cái tầm là hiểu vấn đề lôi ra làm, hiểu vấn đề lôi ra làm thì vừa kịp, mà chỉ cần hiểu vấn đề, chưa hiểu vấn đề lắm phải đi tìm là nó sẽ không kịp. Năm nào thì ra môn đề môn kinh tế vĩ mô thầy cũng rất ngạc nhiên. Tức là mình ngồi mình làm xong, mình ra đề xong mình ngồi mình làm, mình ngắm ok, mình cắt đi mình bỏ vào, mình đoán là sẽ không đứa nào làm hết, nhưng năm nào có vài đứa làm hết. Nó làm hết mà nó còn viết rất đẹp nữa. Hình như có vài năm, năm nào có một hoặc hai đứa làm hết là được. Và là nó hiểu thật sự, vì môn đấy thành như là thầy ra đề như vậy là rất rắn. Cái anh à, đề môn VMAX là rất là dễ, rất là thú vị đúng không?
Nhưng mà em nhớ cái năm 2023 á là có vẻ nhẹ, tức là nếu mà so với năm 2022 thì những lúc đó thì cái tài nguyên mắc 2023 em thấy là ý là vừa sức.
Vừa sức hả?
Nếu mà nói dễ thì không đâu, nhưng mà vừa sức.
Rồi, có thể là thầy cũng bắt đầu già rồi, không còn rắn như hồi trẻ, nhưng mà hồi mới đi dạy rất rất là hay ra những cái đề mà sinh viên sẽ gặp khó, nhưng dần dần mình nghĩ là không cần thiết phải như vậy.
Đó là cái hồi mà em luyện mock test của VMAX á thầy, thì em VMAX á,
Ok. Năm nay thầy có một cái lỗi với lớp, đó là vì thầy bận quá nên thầy đã không dạy pre-master môn macro, và các bạn đã bơi chèo môn của thầy Haliasov đúng không? Không, mọi năm thì thầy sẽ dạy trước, thầy sẽ dạy trước cái phần như Minh Quân thì có sợ gì đâu, Minh Quân với Khiết Anh thì biết rồi.
thầy ASDA, còn thầy Haliasov dạy ASLM.
ISOM thì cũng thế, nó chỉ khác mỗi cái chỗ cái assumption. ISDR là cái market equilibrium là nó restore ngay với thằng ngân hàng chung các bạn. Còn ISLM là mình mặc định là thị trường sẽ từ từ rồi phản ứng, thì về mặt bản chất nó không khác gì cả. Nhưng mà tại sao lại không dùng ISTR, là theo trả lời của Grigory Mankiw là vì nó quen quá rồi, bây giờ đổi thì sinh viên nó khó. Được chưa, các bạn code được hết chưa? Được rồi đúng không? Thầy coi đẹp không? Đó, thấy chưa? Tuyệt vời nhờ. Đấy, bạn Thiết Anh làm được rồi này, bạn Anh gần xong chưa? Đấy, bạn Huy bạn xong rồi này, Huy đã làm xong rồi này. Bạn Chi Trung xong chưa em? Cố gắng. Thầy biết lý do tại sao rồi. Cái thằng bình tĩnh rồi, tôi sẽ tắt cậu. Mình ra chơi đi nhở? Chơi đi, thầy gọi điện cái. Xong chưa Minh Quân? Ô chết, thầy đang mở cái gì đấy à? Sorry.
để cái này.
Tuần sau có cái này, có khi các bạn cái ngày 25/7 á, coi ngân hàng Nam Á bây giờ nó sẽ cấp cái thẻ tín dụng mà không cần chứng minh tài chính cho mình, miễn phí thường niên 1 năm. Thầy nghĩ các em cứ hả? Đấy, quẹt cái vào đóng học phí luôn là không phải vội nhá. Thì là nó sẽ miễn phí cái ngày 25/7 nó sẽ miễn phí cái thẻ visa, cái thẻ mà credit card. Cái này rất là thuận lợi, mấy bạn đi sang Đức cũng vậy. Mấy bạn là trợ lý đó. Ok chưa nào? Thầy phải nhìn thấy đứa nào cũng làm được, thầy mới cho ra chơi đấy. Bạn Lan Thư thế đâu rồi? Chưa chạy được à? Ta còn chạy đúng không? Chắc là em bắt nó chạy nặng quá. Em lấy sample bao nhiêu? Bạn Oanh mở ra coi lót đâu. Không đúng rồi, cái đó em đang làm cheese. Anh làm được chưa em? Đây này, ý tưởng là bây giờ anh đọc lại nha. Bây giờ phải đọc xong phải hiểu, xong làm xong được, tối về kể cho con nghe, thế là nó sẽ nhớ mãi, hiểu không? Bây giờ đi một bước dài nào. Đây là bây giờ bước 1 là phải gì nào? ở đây các bước nào khi mà nhìn thấy cái bài như thế này ha, thì ở đây ý thầy yêu cầu thế này này. Nãy thầy đưa ra thầy giảng cái nội dung là cái mô hình OLS nó có một cái property, là một cái đặc điểm tốt, đó là nó có tính consistent, nghĩa là số liệu của em mà càng lớn thì cái ước lượng của em càng chính xác định nghĩa có nghĩa là cái variance nó nhỏ, đúng không? Bây giờ cái bài này yêu cầu này là em tạo một cái bộ dữ liệu 20 triệu điểm, được chưa? Xong đấy, trong 20 triệu điểm đó, bây giờ là em, ví dụ như em xác định là tôi thử xem là cái sample trong 20 triệu giống như 20 triệu người Việt Nam đi, của 20 triệu người Triều Tiên. Bây giờ cái sample là 200 người hay là 500 người, thì khi mà tôi làm như vậy thì cái error term của nó sẽ lớn vì cái sample nó nhỏ, đúng không? Thì tôi sẽ cho các bạn thấy là cái variance của cái estimate nó rất là rộng, đúng không? Như vậy thì để làm được cái này thì em phải tạo 5.000 lần, mỗi lần làm một sample 500 người, 500 observation. Em ước lượng xong thì em vẽ cái đồ thị của 5.000 lần này lên để thấy. Trong đó em lại tăng cái sample size lên từ 500 em lên 1.000, được chưa? Em lại lặp lại 5.000 lần, rồi em graph hai cái tập hợp 5.000 lần của một cái là một cái là sample size 500, một cái là sample size 1.000 cùng lên một cái đồ thị để em xem cái sự khác biệt về cái variance của nó, đúng không? Đó, rồi đó. Vậy thì đây đây thì cái bước làm nó sẽ như thế này. Cái bước làm sẽ như thế này. Đầu tiên em xem nào. Đây, đầu tiên là thầy phải set đâu nhỉ? Set cái seed này, để làm gì? Cái seed này trong bản chất của cái vấn đề khi mình tạo cái random number, nó không bao giờ random, nó phải ông tạo ra random sum. Vậy thì bây giờ nó có một cái cách làm ngẫu nhiên, cái random number generator. Nếu như mà em mà không nói gì thì mỗi lần nó sẽ xuất phát từ một chỗ khác nhau, và nó sẽ dẫn đến cái tình trạng là em sẽ không bao giờ lần này em chạy xong ra kết quả này, lần sau nó khác gì. Nhưng nếu em set cái seed này có nghĩa là nó sẽ luôn luôn bắt đầu từ cái vị trí này, cho nên là em simulate nhiều lần thì kết quả nó vẫn giống nhau. Nên ý tưởng vậy thôi nhá. Rồi, bước 1 là gì? Simulate a 2 million. Ở đây thầy có lấy 2 million observation thôi cho nó dễ, được không? 2 million observation là epsilon. Thầy đặt n là bằng 2 triệu, được chưa? Epsilon chính là cái epsilon ta hay nói đó. Là thầy dùng cái random là cái library NP này, random này, normal này, mean là bằng 0 này, variance bằng 1 này. Cái size bao nhiêu dòng, n dòng. Được chưa? Thứ hai là tạo thành cái biến x2, mình nhìn thế này này. Mình nhìn trên cái mô hình mà mình cái starting point của mình á, là nó bằng beta 1 cộng với x2t mà, thấy không? Thì mình sẽ tạo, mình không phải tạo bài biến beta 1 bởi vì là cái constant, mình chỉ tạo cái thứ hai rồi. Đó, thì ở đây mình sẽ tạo x2 là cũng là bằng gì? Random, nhưng mà cái số này mình cho là chi-square, 4 degree of freedom, được chưa? Sai chẳng nhé. Cái constant thì bằng np1 n là nó thành cái cột 1 rồi. Sau đó thầy nói là y thì bằng 4 nhân với constant, 3 nhân với 2 cộng với epsilon. Đây là cái mối quan hệ này này. Cái mối quan hệ này là mối quan hệ ta biết là cái relationship. Rồi, ta biết cái này, ta tạo cái này coi như ta biết cái này là thật rồi, đúng không? Thấy cái này thật rồi, không có phải gọi là lo lắng gì là không biết cái mối quan hệ này có đúng hay không. Okay, so I keep running it. Let's see. Okay. Đang mưa vậy, cẩn thận nhá. Đây, thầy chạy xong cái nó xong luôn, nó ra luôn rồi đây này. Như vậy là bây giờ là có một cái mối quan hệ relationship trong cái bộ dữ liệu này, ta biết có một quan hệ thật là y thì bằng với gì? 4 cộng với 3 nhân x2. Rồi. Nhưng bây giờ ta giả vờ ta không biết, ta phải ước lượng cái mối quan hệ. Vậy thì ta phải đi lấy một cái sample. Đúng không? Ta lấy sample 500. Được không? Lấy sample 500. Ví dụ trong trường hợp này, mình lấy sample 500. Dạ, ok. Ok, sau khi mình tạo xong thì mình đưa nó vào cái data frame, phải đưa nó vào data frame thì nó mới thành bảng như bảng Excel được, cứ đưa ra ngoài được đúng không? Rồi, ok. Rồi là data frame to full to CSV thì thầy chỉ tạo ra cái biến thì không sao cả. Đây rồi, chỗ này là như thế này. Bây giờ ở đây á là cái sample size. Sample size này ở đây thì mình sẽ tạo các mình sẽ tạo simulate trên các sample size. Sample size là 100. 100 là nhiều hay ít? 2 triệu mà 100 là ít, đúng không? Rồi bây giờ em lấy một cái sample 100, em tính ra beta 2. Lấy cái sample 100 khác, tính ra beta 2. Lấy cái sample 100 khác, tính ra beta 2. Ta biết beta 2 bằng mấy? 3. Em tính 5.000 lần xem thì nó sẽ lúc thì lớn hơn 3, lúc thì nhỏ hơn 3, có đúng không? Nó nhảy xung quanh con 3. Vậy thì ta xem cái độ phân tán của nó giữa hai bên con 3 ấy như thế nào. Được chưa? Sau đó ta lại tăng cái điểm lên 200 điểm dữ liệu là 500 điểm đó. Vậy thì bây giờ cái cách tốt nhất là để làm cho nó nhanh á, để làm cho nó nhanh trong trường hợp này á, thì thầy nghĩ là cách làm như thế này, nếu không thì mà đợi nó chạy xong rồi sáng mai chúng ta mới được về, đúng không? Đó. Bây giờ thầy sẽ làm như thế này, là cái đội mà trên thầy chỉ lấy khoảng độ 5.000 thôi, lấy mấy cái điểm này thôi. Thì bây giờ là thầy sẽ demonstrate cho anh thấy ha. Thầy chỉ lấy 10.000 thôi, được chưa? 10.000. Như vậy là bây giờ 10.000 và mỗi một cái lần mà mỗi một cái sample này là ta hãy nhớ là mình trả lời ban sáng là expectation là gì? Là tôi lấy nhiều sample. Thế cái nhiều đó là bao nhiêu? Thì ở đây thầy đang yêu cầu là 5.000. Thì thầy nghĩ là 5.000 này nó chạy cái này chạy 5.000 nó chạy lâu lắm, thầy lấy 500 thôi nhá. Hiểu không? Được không? Sample size là 500 thôi, được chưa? Đó. Rồi. Như vậy là với cái sample là 100, nó sẽ draw 100 bất kỳ trong hai triệu điểm dư nó lên 100. Nó tính ra beta 2 nó xếp vào. Làm lần nữa, nó làm 500 lần. Được không? 500 lần. Đó. Đây như vậy là làm 500 lần. Thì như vậy là cứ mỗi một cái data small này, data full này, data small này là nó chỉ lấy 500 điểm dữ liệu thôi. Xong 500 điểm dữ liệu này thì nó sẽ làm sao ạ? Nó sẽ ước lượng. Thầy chỉ lấy đến 10.000 đúng không? Thầy bỏ cái bọn này đi. Rồi, ok. Đấy, nó nói là gì? Kim thầy không đến 5.000 mà chỉ lấy 500 thôi, thì bây giờ chỉ được 500. Với consistent, nếu không là nó sẽ không chạy. Rồi, bây giờ nhìn này. For này, bắt đầu nhìn nhá. For J in the range 500. Có nghĩa là bây giờ em có cái bảng dữ liệu như thế này. Cái dòng đầu tiên này này. Trong 500 dòng em mình tạo đúng không? Dòng đầu tiên. For J là 500. Thấy chưa? Sample thì đầu tiên là sample df là bằng df full sample size là bằng n là bằng size này. Xong là mình perform the OAS regression là mình chạy cái regression đúng không? Xong đó mình sẽ lấy cái parameter của b của x2 đấy, mình bỏ nó vào cái location của nó là bằng j, và size này là chính là cái số lần mà cái số lần mà mình sẽ simulate. Rồi bây giờ mình chạy. Đó. Thì khi mình chạy xong mà mình không thấy nó nói gì thế này là đang làm gì ạ? Nó đang chạy, nó đang còn randomly draw nó nhỉ? Cái nhìn thấy không nhỉ? Đó. Thì khi mà mình làm cái này nó chạy xong được đủ bộ dữ liệu, đúng không? Thì mình sang bước tiếp theo là gì? Sang bước tiếp theo là mình sẽ tính cái kernel density của nó. Này. Ok. Thì ở trong trường hợp này là với các cái B này, đầu tiên là với B100 này, B200 này, B500 và B1000 này, thầy làm cho một cái đội này đã, đúng không? Rồi thì min và max này, thầy đố bạn anh là cái min này và max này và cái min này và max này, cái nào nhỏ hơn? Cái min này và cái min này cái nào nhỏ hơn? Nào, suy luận nào, bạn Khiết Anh. Cái thằng min của 100 của cái sample 1000 và thằng min của sample 100, thằng nào nhỏ hơn? Trả lời chừng rồi. Nào bạn Minh Quân. Tại sao? Cái min nó thấp hơn đúng không? Đây đúng không? Đây là vị trí là 3. Thằng 100 thì nó như thế này. Đúng không? Còn thằng 1000 thì làm sao? Như vậy thằng 1000 thì cái min của nó ở đâu? Ở đây. Còn thằng 100 thì cái min của nó ở thằng nào nhỏ hơn? 100 nhỏ hơn đúng không? Max thì thằng nào nhỏ hơn? Thằng 100. Max. Bởi vì cái khoảng của nó làm sao ạ? Khoảng nó rộng. Khi mà sample mà lớn lên thì cái độ phân tán của nó nhỏ xuống, nghĩa là mình ứng dụng tốt hơn hay sẽ đi tốt hơn, hiểu vấn đề không? Xong chưa? Ôi trời ạ, vẫn chưa xong. Ok nhá, thầy đã share cái file lên share folder rồi. Nhưng mà sau khi chạy xong thì kết luận lại là nó sẽ được như thế này. Đó, thầy sẽ gửi các cái file có cả rồi các em về tự eyeballing để nghiên cứu nha. Thì ý tưởng các em nhìn này đây này. Cái bạn này là 100 đúng không? Thì cái min của nó ở đây. Bạn này là 1000 này, 1000 là bạn màu đỏ, cái min ở đây này. Hiểu vấn đề của cái consistency không? Nếu mà các em program được một lần, Khiết Anh thì làm được rồi đúng không? Khiết Anh là một trong những bạn đầu tiên làm được. Bạn Huy cũng làm được rồi, em làm được chưa? Được rồi. Bạn Tuyền đang còn chạy à? Đó. Bạn Anh chưa xong đúng không? Bạn Anh ngày mai thì sẽ kiểm tra đầu giờ sáng cho bạn anh làm xong chưa? Làm xong anh về eyeballing thì cứ từng làm xong được thì mình sẽ hiểu rất nhiều về cái programming nhá. Đấy, cái programming nó có là gì đâu. Bây giờ có thể anh thì còn rơi vào tình huống giống như sinh viên đặc biệt nhà thầy, là đợt mà làm Python xong không được đập bàn, nó nhớ sao hết được những cái function này. Chứ bây giờ không phải nhớ, hiểu không? Nhưng mà cứ xem mãi thì mình phát triển một cái thói quen với nó, rồi khi mình cần cái gì thì mình gọi thôi, đúng không? Tức là em đừng, nếu mà ai đấy trong lớp này bây giờ đang có tâm lý là tôi sẽ nhớ bằng được thì không cần nhá, nhưng mà mình cũng nhớ một số, đúng không nhỉ? Mình nhớ cái logic của nó, ok không? Good. I already uploaded. Yeah. Don't you see it? Yes, I have just uploaded. Yeah, its name is demonstrating consistency demonstration. Or it is still uploading. I'm sorry, but say it won't be there, right? So basically, you follow the steps, and you see that why it is estimated in this way. So yeah, basically, this is when I put all of the samples together. You see, so in the beginning, 100, a sample of 100 is on this side, but then it goes quickly to one line. When it is this case, we say that the distribution degenerates into a single point. Good. Good. So let's say that is one part. Now the BIC and the so let's say basically I'm not going to repeat this part, right? I'm not going to repeat this part because it won't be too boring for you guys. You already know, right? So let's say basically the idea of the maximum likelihood is to choose the value. So let's say the maximum likelihood estimation is based on the specification of the model through the joint PDF probability density function Fy theta. So generally speaking, when you know F, when you know theta, you won't be able to get the one. Okay, that is the probability density function. Probability density function. So when you know the Y, I'm sorry, when you know the F, you know the theta. The F is like normal. Theta will be mean and variance. If you know this is normal, mean is 5, variance 10, you can get all the Y that you want. Is that right? Get it? So this is the probability density. Okay, good. When theta is fixed, the function dot theta of Y is interpreted as the PDF of Y, the probability density function of Y. Right? So when you know this one, you will be able to get the Y. Now, but if instead we view the function Fy theta evaluated at the n vector Y, then the function Fy dot theta here of the model parameters can no longer be interpreted as the PDF, but it is the likelihood. So the likelihood function is the question. If you have that data already, the probability is have the function, find the data. Now you have the data already. Okay, so you will choose the value of theta. So the likelihood of getting that data set is largest. Okay. Okay. So let's say this is the idea of the likelihood. The probability density function is the function when you know the parameters and use the function to generate the data. The likelihood function is when you have the data and you want to choose the parameter, so the likelihood of repeating that data set again is highest. Okay, that is the likelihood function. So the maximum likelihood estimation then amounts to maximizing the likelihood function with respect to the parameters. A parameter vector theta at which the likelihood takes on its maximum value is called the maximum likelihood estimate, or LME, of the parameters. Fair enough? Definition wise, okay. Okay, so let's say we already have this, right? So this is now if you have a sequence of data, each observation of Y is generated following a probability density. Then if you have n Y, and if as we assume that if they are independent, then the probability is the product of the density. Yeah, the joint density is the product of the density. So this is the part that you would define the likelihood is the log likelihood. That is to take the log. When it is the product, if you take the log, it will become the sum, right? This is something you already know. And so, for example, if we now have the we assume that our epsilon follows a normal distribution with mean 0 and variance sigma square times I. This is when it is sigma square times I, it is identical and independently distributed, because of the diagonal there is no covariance. Okay, on the diagonal it is always sigma square. Right. So that's the idea of AID. And the density of one observation could be written in this way, right? So if you have n observations, if you take the log, it will be of this one. And if you have n observations, you sum them together, it will be of this formula. So if you forget about it, please sit down and take a pen and a piece of paper and write it down. So if you want to maximize something, remember that from our discussion on calculus. If you want to maximize something, you find the tangent line. That when the tangent line is horizontal, it could be either be a maximization, a minimization, or something of a combination, right? We call it a saddle point. So the first step is to set the first order of condition to be equal to 0. And if we do that, we get this one, right? This is the first order. This is the another first order. So you can do it on your own, but basically beta and sigma are the same. Now, so this introduction here is just meant to so let's say for in terms of the maximum likelihood estimator. Some further information about the second order derivative is known as the information matrix, and it's the variance of the first order. Let's say that's something you have to read. But basically, what I want to do is here at the maximum point, the log likelihood function. The likelihood function is evaluated and could be shown to be equal to this one. Okay, so this is what you have from the log likelihood, the likelihood function. So you have the likelihood function, right? You have the likelihood function of this one. Now we come to the definition, right? So if you have the AIC, the AIC is defined as equal to 2 minus 2 log of the likelihood function plus 2k, right? Now go back to this one. So what is the value of and the BIC is equal to this one, and the likelihood function is here. At the maximum point, you take the estimated error term, right? This is total. This is nothing more than, let's say this is nothing more than the total sum of square. Is that correct? To the power minus n over 2. Okay, so you can, even if you don't estimate, you have not, because we have not reached the maximization part yet. Even if you don't run the optimization to maximize the likelihood function, you know how it can be computed, right? It is the total sum of square. So even if we run the OLS that we have been computing so far, right, we can also compute the log likelihood, which is equal to this one, right? Okay, so let's say it takes me a lot of efforts to go to this point, but the purpose is only that so that you implement this line into Python. Correct? It takes a lot of effort just to do a little thing. But let's say if I don't go from here and I just tell you compute the log likelihood, the likelihood function in this way, you would start asking me how, right? So this is the reason we go through that. And you see that the AIC is defined in this way, the BIC is defined in this way, right? So if we know the BIC and the AIC, what they are, it is done. But we move on already. So the thing is, sometimes we need it, but it's not fast enough, it goes wasted, right? So they have to, the software has to take the opportunity to be shown, otherwise we ignore it. But let's say basically, ladies and gentlemen, this is the AIC and this is the BIC. Right? Good? Yes. Now, have a look again here. The AIC is, so we want to maximize this one, right? We want to maximize this one. Now just have a look here so that we get the information. When we want to maximize this one, right? So it will be the absolute value should be as small as possible. And most of the time, the likelihood function would be negative. Okay, so if this is 0, you maximize it, it will move closer to 0, but it could never be 0. So you take the negative, it will be positive. Okay, but if it is maximized, this one will be small. Okay, the absolute value will be small. So in this case, we would look for the AIC that is as small as. Yeah. Similarly, the BIC also is as small as. And so if we have two competing models, and one has a smaller AIC, then we would prefer the one which has smaller AIC, right? Just similar for the BIC. So I put the difference between the two for your answer. Okay. So we already covered this, right? Don't you think that because this is not an econometric course, right? This is never an econometric course. Please compute the likelihood function and the AIC and the BIC and compare. We are studying Python, right? Implemented, right? So now the next job is compute the likelihood function and compare with the original one. Khi mà thầy đi cái phần lý thuyết này gợi lại như thế này thì có nhanh quá không? Ok đúng không? Chịu khó về nhà xem lại ha. Cái thầy mà đi chậm mà giải thích hết được không? Lên rồi. Chưa lên à? Chưa lên thì có khả năng là do mạng à? Custom gì đấy? Download. Có thể Binder hả? Môn này thì chắc là những kiến thức đã biết rồi và áp dụng nó vào Python. Nhưng mà Binder thì Binder rất hay dùng AIC và BIC. Nó khác nhau đây em ạ. Em muốn nói đến cái HF gì đó đúng không? Trong mấy cái information criterion thì còn có AIC này, BIC này và một cái là H thì nó khác với em. Hả? Hay là mình có khác? Hay là muốn nói đến cái nào?
Ý là BIC là nó còn có một cách viết khác là SBC mà trên Google thì nó dùng chỉ là cái cách nói khác thôi chứ cùng một công thức.
SBC. Thì chắc là có ai đây gọi một cái tên khác đúng không? Nào, các em implement cái này vào trong Python. Đàn từ gọi đây là có. Anh có người khai à? Ok rồi, thầy xin lỗi. Thầy thấy đang chat với bạn Phú Mỹ rõ ràng rồi. Ok, nào để thầy coi 2024 đâu nhỉ? Thầy share cái file này. Ôi sao thầy up mà nó không lên à? GFE. À không, thầy không up được video ấy đâu, vì bữa đó thầy về nó bị thầy quyết định là thầy sẽ cài lại cái máy, và khi thầy cài xong thì phát hiện ra có mấy thứ thầy đã không save, mặc dù lúc cái số save thì thầy đã save rồi. Bữa đấy nó đem nó ghi vào cái file vào cái folder document, thầy quên mất, cho nên là cái ngày thứ hai thầy sẽ không có video đâu. Sorry. Today I won't have one. Okay. For some reason, I have to admit that that I would I made a mistake. It was still synchronizing. Okay, so I will also share the consistency demonstration just in case I can do that. Good. And now I will also share the second day script, right? So that you have them all. Okay. Okay. Can you implement this calculation and then so how to get the numpy the pi the number pi here? How to get the number pi here? Number here is number np dot pi. That is, I think to be honest, if we do this into light into ChatGPT, we won't get it at no time in no time, right? This one, computers. I have named the residual as what is it? E underscore hat. A mistake, I think. Biết ngay mà. Let's say computers give me Python code to okay. Okay, let me put it down here. Oh no. AIC then BIC, right? Where is it? AIC and BIC down here. Oh, likelihood ratio test and okay here. Oh no, it's the likelihood ratio. Is that correct? Okay, I already did the calculation here. So this is the code that we would need to. The likelihood is equal to this one, exactly what we do. So now the only thing is that I have created the sum of square of the other term. So this should be done in no time, right? Results too large. What's that? Did you get the same problem? Uh-huh. Let's see. Let's see. Overflow error. Let's see what the problem is. Okay, so the idea is that it will, if we compute the log likelihood, the likelihood function, it could be very large. So let's compute the log. So let's say you have the log, and I hope that it will be good. So the log likelihood is minus 9,322. Thì đố các bạn tại sao cái log likelihood lại negative? Tại sao log likelihood? Tại sao cái log likelihood lại negative? Log likelihood nào? Đó là cái log của cái likelihood của likelihood function, đúng không? Nào, thầy hỏi các bạn, cái likelihood function nó lớn hơn 1 hay nhỏ hơn? Lớn hay nhỏ? Nhỏ hơn 1 và log thì âm hay dương? Âm mà bạn sắp nhiều lần lại thì nó phải không âm không biết, đúng không? Được vấn đề không? Đồng ý không? Yeah. Okay. Probability thì đóng ok. Nào, ban nãy cái file thầy share đấy chắc là nó sẽ xếp lên ha. Ban nãy là thầy không tính cái log likelihood, thầy làm lại như thế này để các bạn thấy này. Nãy là thầy tính cái likelihood mà thầy cũng không để ý, thầy chỉ tính thôi, thầy chỉ viết ra thôi mà thầy không để ý. Nhưng mà vấn đề là nó không tính được, vì sao ạ? Đây này, trên cái máy tính của mình nó chỉ nhớ được bao nhiêu con số thôi. Thế nên chỗ này thầy nghĩ là chỗ này khi mà nó bảo video quá lớn ấy, thì chắc mà là quá lớn đâu, mà cái gì đó mà mũ trừ n trên 2 đây là mũ trừ 4.000, đúng không? Mũ trừ 4.000 thì sẽ tạo ra con số vô cùng nhỏ, nhỏ tới mức mà cái máy tính nó không nhớ được. Cho nên nó bảo là cái dãy số bạn nó Các bạn thấy cái log thì nó cái chỗ này là vấn đề kỹ thuật ha. Okay không? Good, everything is fine. So it took me a lot of time just to do several lines. So again, programming is to write down something that you already know. So the computer just tapping in terms of number of functions. It will not help. It cannot help us in terms of knowledge. Again, you need to know that in order to do the calculation. Okay, so I'm done with the AIC and the BIC. The F test I already did. Oh, bravo. I think the LR statistics. Now I talk about we talk about the world test, right? Now, ladies and gentlemen, this one is known as the world test. Yeah. Sorry, there is a okay. So let's say right. So the F test in this way, the F test in this way is known as the world test. So what is the world test? The world test, the idea of the world test is to say if you have the theta, let's say you are interested in estimating theta, okay, and you have a theta hat and you hypothesize it as theta. So the world test will ask how far or how further or how different is it between theta and theta, right? So let's say if you have a variance covariance matrix omega, so basically the idea is this one. If they are pretty close, okay, the difference are just simply the random differences, then this one will follow a guide. If they are systematically different, this one will be large and will not follow. That's the idea of the world. Yes. Branch test. Cái vô test, cái test này là test hai đó là vô test. Từ này ví dụ như này là test cho cái app test theo regression table. Nó gọi là gì? Nó gọi là cái vô test là một cái phương pháp luận. Thế là trong cái context graduate test là cái context của như vậy cái này gọi là world test cho nên là chỗ này đặt là cái tên là để mà okay, in order to test for the same hypothesis we can also use the so-called Lagrangian test, LR test. So this is the likelihood ratio test. Okay, so for the same purpose, now we are interested in testing R beta equals to Q. We don't use the world test anymore, we use some other test. This test is known as the, I'm sorry for the, I use this one in another. So let's say we have the LR test defined in this way. So the lambda here is the let's say we have the likelihood ratio evaluated as the for the unrestricted model and for the restricted model. Okay, then the LR test is defined as equal to this expression here, and it will follow a chi-square with Q. So I have prepared some of the steps here, but basically the LR test is based on the likelihood evaluated. So this is the LR, right? So if you use this one, you compute the LR. This one will follow a chi-square Q equilibrium. Q is a number of the likelihood. So I will go to the LM test. Then we compute the LR and LM, and I think the afternoon is already rich enough. So the LM test, and then we come back to the case. So again, we have a the same hypothesis again. So we have a model that is y equal to x beta plus epsilon. Epsilon follow a normally distributed process, which means zero invariant sigma square times IM. Fair? The question is, we want to test R beta times is equal to R, right? Or let's say Q. Then let's say I use. So let's now we will approach the issue from the perspective of a constraint optimization. So in the OLS model, right, you have this minimization problem without this part here. Let's say without this one. You have just have that. Okay. In comparison with the OLS model, we have a constraint. Okay. Good. So let's denote the restricted estimator, and using the method of Lagrangian multiplier, we will have this one is nothing more than the Lagrangian function, right? It is equal to the affected the function plus the constraint. So what do we do? Take the first order. We come back to line again, right? So let's say if you take the first order with respect to beta, you get this one. If we take the first order with respect to the Lagrangian multiplier, we have this one, and we will follow certain derivation here, and finally we will have that beta star is the restricted one, is equal to b star equal to b. This is the unrestricted one, right? Plus this component. So we can go from here to here on the own. So let's say I am deriving another test from the perspective of the constraint optimization, right? So you define the unrestricted error term. I will use epsilon also, but let's say it will in this context I use G, but then epsilon E star is the restricted term, and it would be shown that E star is right. So E star transpose E star is equal to this component here. So in the increase in the restricted sum of square of the error term is this part, right? So it is equal to component. And if we take b minus b, b star minus b over here, here, right? We plug it in this one, we will get the total sum of square of the restricted model minus the total sum of square of the unrestricted model. You will have an expression that is look like this one, right? And again, we can define the Lagrangian multiplier test as equal to this component here. And you may notice that the Lagrangian can be rewritten in this way. So this is sigma hat square. So it is this one is divided. It will be equal to n times plus. So its asymptotic distribution can be shown to be to follow a chi-square with RD here. So let's say this is, so basically the message here is the message.
Thầy ơi, hình như cái mic của thầy hết pin hay sao á, em nghe không có rõ lắm đó thầy.
Oh, for some reason I put it away when I was writing. Can you hear me now?
Yes, yes.
Better now? Okay. It is out of battery, I guess. Let me turn on the other one. Okay. Can you hear me better now, Linh?
Yes, yes.
That is when I sit down here, right? So let's say I'm going to connect it. That is no, I think this one is still okay, right? Can you hear me now? Hello.
Yes, doctor.
Okay. Okay, good. So basically, what I have done so far, I would request you to go through the derivation again. But the steps here is to tell you that if you follow the constraint optimization approach, you will in the end find that the LM statistics can be computed as n times r squared. Okay, so let me explain how this could be because if you don't if I don't do this tomorrow when we talk about the generalized least square, you will ask me where does it come from, right? Oh, let me do it on the screen because you will not be able to see it, right? So basically, what I want to say is this one. Tomorrow, and it's especially in many texts, right? In many of the textbooks that you may encounter, this could happen. So do you remember the problem of heterogeneity? Right. So let me do this, and for the thickness, I just make it out. It can be one immediately. No, it doesn't work that way. Now, let me explain the context, and then you understand why, right? Nice. $26. Okay, so when do we have? So let's say all of the steps that I have shown here, I deliberately included the steps that are very much in detail because I know that I would not have all the time to explain, right? But let's say, why do we care about the fact that it is equal to n minus r squared? So let's say let's talk about the GOS. Right, the GOS. So what is the specification of the GOS? Is y equal to x beta plus epsilon, where epsilon is normal, is distributed IID, which means mean 0 and variance omega. Okay, and omega here is equal to sigma. Let's say it would not work that way. So let's say it will be something like sigma 1 square 0 0 0 0 sigma 2 square 0 0 dot dot dot. You have 0 0 0 dot 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 sigma n square. So this is the problem of heteroscedasticity, meaning that the variance of each observation. Tomorrow we will learn how to write a heteroscedasticity consistent variance covariance matrix, right? But let's say let's move to the realm of GLS. Yeah. So when we have this one, the question when we doubt that the variance of on the diagonal are not constant, what do? We will depends, or let's say they depends on the value of x's. So let's say we will extract a vector. Let's say we take a vector. Let's say vector sigma, right? So let's say I put it vector sigma square. So sigma square as a vector. I put a v here. And of course, we will take the log of sigma square. Our question is, we want to know whether the log of sigma square varies with the independent variable. So we will run a regression, right? We want a regression that where the log of sigma square is equal to gamma 1 plus x times let's say let's say gamma 1 plus gamma 2 times x2 plus gamma 3 times x3 plus dot 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 plus gamma k times xk. This is not, we don't just stop there. And we will have, it will be delta times x1, let's say delta I j times the let's say plus the summation delta I just times xi times xj. Okay, so we want to know if the variance, the log of the variance vary along any dimension of this, right? So normally you will see it is of course plus an error term plus okay, let's say a CI. Now normally in books like by Woolrich, they run this regression and they will compute, they get the R square, they run this regression, they get the R square, okay? And they will compute the LM equal to n times R square. And this one is asymptotically distributed as chi-square with 1 degree of freedom. Okay. So let's say if we do not study the LM before, and then when you read a simple text like a Woolrich, you will start wondering, so how can people do this? How can people take n number of observations times the R square in this auxiliary regression? Okay. The idea here is nothing more. We are, if this one is constant, then the coefficients of this one, and all of this one must be what? 0, right? 0. So you are testing all of these ones. Is that right? So this is the idea that we need the LR test in that way. So when we basically when we apply the test, the idea of the LR test comes from the Lagrangian multiplier, and this is where it comes from. And tomorrow, and in many of the texts, maybe at the other contexts when people do not study econometric in a rigorous way, your professor may say, if we do this, we will have the something called the LM statistics. It follows a chi-square distribution with one degree of freedom, right? In our context, it is it follows the proof that we have done in the previous slides. Right? So this is the LM test. And the origins of the LM-LR that you often see when you do the econometrics. Okay, so I took an example here, but it's just for you when you want to deepen your knowledge. This is very much something that I look forward to if you intend to become a researcher in the future. So these are foundational knowledge that you should remember. And this is something that I want to patch because I went through the curriculum and I didn't see anywhere that we cover this. So let's say, but again, I don't see the other way of teaching Python without deriving the results and then implement it. Right? So you see that when we know the theory and we can derive the results, then computing the test statistics and all kind of statistics in the regression analysis is quite simple. It boils down to this result, right? So actually the software is quite stupid. He doesn't do a lot, right? If we have to do all the work, we just do the simple one. Right? So let's say this is somewhere we have to move on. Good. So please have a look at the LM-LR and again, this is a Ramsey test, right? The Ramsey test. Oh, let's now let's stop here and compute the test, the LM-LR and okay, let's go back to it's 10 minutes left. I don't move on to the other okay, so let's stop here today. Right? I intended to move on to the GOS and the VIF. You know the VIF? I mentioned it right at the beginning. So now we have to compute it. We will prove the VIF and we also do the Ramsey reset test. Reset test. Now the Ramsey reset test would use the world test, right? So basically the idea that tomorrow we will start on fixing the violations of the OLS assumption. We would move on to the GOS and the IV. In the afternoon, we will have only one afternoon to talk about the optimization, but that doesn't matter. I think in the end, if I already derived the mathematical results, it's only yours to learn. Okay, so it's simple. But let's say for now, let's do something different, right? So let's say for now, unrestricted estimates. Okay. So I have prepared the code for the LM and the LR test here, right? The LM and the LR test here. So let's say for the LR and the LM test, the first one is to say we have the model that when the dependent variable is the log of expenditure on clothing, the set of variable x that is unrestricted include the log of total income, corruption of if the household is corruptible with a member working for the public administration, the ethnicity of the family of the households, and if the head of the household is married. So let's say we define some number here. So x, this is the x unrestricted, and with this one I have just turned it to a matrix, nothing more. Then I have the k unrestricted is equal to the shape. So when you say x unrestricted, the shape equal to 0 is the number of rows. When the shape 1 is the number of columns. Good. And now we define the restricted sample, right? At the restricted model, right? And we define the restricted model. So the restricted model is nothing more than this one. So basically, in the restricted model, we don't have the yeah, we just have some less two less variables basically, right? So again, we define it in this way. So we estimated both models manually. So I would expect you, if you have time, right, at home, sit down and type all of them once more. So develop the sense of coding. Actually, when I started learning Python, I did that. I went through one whole book, and then I got used to it. Right? And then I would compute the LR test start, right? So if you have this one, you will be able to compute the the likelihood function ratio. And then the likelihood ratio is defined in this way. We already know in the formula. So it's just the implementation of the formula on the slides. So the number of degrees of freedom is equal to the number of restrictions. So we can compute the p-value of the LR, that is 1 minus the chi-square of the CDF of the. I'll start here, right? So this is the implementation. This is the implementation of the steps here. So let's say I started with what is the maximum likelihood, and then here is the definition of the LR. You see, right? So it is the LR test is defined in this way, and we just simply apply that into Python, right? Nothing more. Good. And then I use the LM test, right? So the LM test, this is nothing more than the step to replicate the mathematical derivation about the LR, right? So let's say we would have the LM start here is equal to right. So let's say this is the definition, and it follows the LM step. The LM here is computed using this formula, right? Yeah, the LM is computed using this formula, and if you implement this one into Python, you will get the answer. So basically, what you need to do now is eyeballing through the LM and the LR and connect with the mathematical. But let's say there is not a lot more than that that I can say. Either you want me to talk about the VIF and the Ramsey reset test now, or you want to, I see that you are tired, right? Are you? Yes. Rồi, nói chung là chúng ta sẽ quay lại đúng cái thôi thầy sẽ cắt ngắn cái phần optimization, nhưng mà thầy sẽ đưa cái ý tưởng. Ngày mai chúng ta sẽ sang đến phần GLS, và phần GLS này, phần panel này, và phần endogenous variable trong buổi sáng. Buổi chiều thầy sẽ dạy về optimization. Cái ý tưởng là ngày mai mình lại ước lượng cái mô hình OLS bằng một cách khác, là mình optimize nó. Thế xong mình compare là bây giờ mình đi cái gì nào, cái phương pháp chúng ta vừa làm bây giờ nãy giờ ạ, là chúng ta derive ra công thức, chúng ta dùng gọi là closed form solution. Nhưng mà đời không phải như mơ, không phải lúc nào nó có như vậy. Với rất nhiều phần lớn là chúng ta không có cái closed form solution. Vậy thì ta phải đi dùng một cái biện pháp là numerical optimization để mình tìm cái điểm nào là cái điểm lớn nhất của cái maximum likelihood function. Vậy thì ngày mai mình sẽ đi ngược lại. Và bây giờ bữa nay này là mình dùng closed form rồi mình đi tính cái likelihood function, đúng không? Mai là mình đi maximize cái likelihood function, rồi mình quay lại mình đi tìm cái qua cái quá trình maximize đó thì mình sẽ tìm ra cái giá trị beta và sigma square, được không? Tức là mình sẽ đi một cái hướng hoàn toàn khác nhỉ. Rồi thì ngày mai mình sẽ làm được đó, xong rồi mình sẽ derive cái optimization cho cái mô hình AR1. Nếu mà có thời gian thầy sẽ làm thêm cái thầy cố gắng derive ra. Nếu mà đã derive về xong nói 2 phút rồi đưa ra code thì có gì đâu, code thì ChatGPT làm, đúng không? Bây giờ có toán là ChatGPT làm mà, đúng không nhỉ? Tóm lại là cái toán nó giống như cái guiding vậy. Đấy, vậy thì bây giờ các em chịu khó xem lại cái phần discussion từ phần 1 đến sang phần 2, đúng không nhỉ? Phần 2 ngày mai, cái phần 2 đây thầy chỉ thêm mỗi cái phần optimization là hết thôi. Thứ tư chúng ta nghỉ để đọc cái bài replication. Thứ năm, thứ sáu thầy sẽ đi từng bước một replicate nó cùng các em. Ví dụ như bây giờ chúng ta đặt ra câu mục tiêu là chúng ta bây giờ cần compute cái A, cái B, cái C, chúng ta sẽ compute như thế nào. Thì đến thứ sáu là chúng ta sẽ có một bộ dữ liệu mà nó giống như là bộ dữ liệu đó trên Stata. Đấy, thì xong đó chúng ta sẽ nghỉ, và em sẽ vào học lớp của thầy mới đi. Trong quá trình đó các em lại dùng Python lần nữa. Đó, các em lại dùng Python lần nữa thì để trong phần lớn thời gian thầy nghĩ là maybe thì sẽ không có tính bằng tay mà sẽ tính cái routine sẵn rồi, bởi vì nó có mục tiêu của nó lại không phải là học Python nữa, đúng không nhỉ? Lại học là kinh tế học tài chính, đôi khi sẽ phải tính toán một số. Xong sau đó thầy sẽ đưa cái lịch thi và lịch học hai cái buổi cuối cùng để các em presentation, một ngày cuối cùng để các em present. 9 người present. Thầy đang để present là thầy để một ngày hay là thầy để 2 ngày nhỉ? Thầy để 1 ngày rưỡi. Về chưa hả? Ok, xong rồi về thôi. Các bạn là mình đến 1 ngày rưỡi thì chắc là buổi sáng mình sẽ có 6 người trình 1 ngày rưỡi. 1 ngày rưỡi thì ok. Mình sẽ sắp ra cuối cùng sau khi Medi thi xong môn của Medi mình sẽ gặp lại nhau 2 ngày nữa thì sẽ không. Ok, như vậy là hôm nay rất nhiều kiến thức ha. Hôm nay rất nhiều kiến thức. Thầy đã post cái file lên rồi mà tại sao nó chưa lên? Uploading mà nó không cho lạ nhỉ. Hello Linh.
Dạ thầy.
Okay, so we stop here, right? So let's say please have a look at the slides and the codes today, right?
Yeah, of course.
Okay, good. So we stop here, and I hope that you will be better tomorrow, and see you.
Yeah, see you tomorrow. Dr. Han.
Bye bye.
Thank you for today.
My pleasure. Bye bye.